If I have a distance function which in this case the s is the height after t seconds in feet. Something like that. If this represents a distance function, a height function in this case, after t seconds, way back when, we were still doing tables when we last talked about this, but remember what we did was we took a look at a table, we took height after 1 second, and then we went to 2 seconds, then we shortened it to 1.5 seconds, then 1 to... Well, that wound up giving us velocity, didn't it? Instantaneous velocity, we called it. Well, we could do the same thing now, but with derivatives. You know, if I do my average velocity here from time t to t plus h, t plus a little bit. Well, it's the difference of the distances over the difference of the times, which winds up being h. Then if I shrink a to be, h, let the h shrink to 0, h go to 0 of this. It's just distance again divided by time. This is t plus h minus t. That's why that's h. Anyway, I just wanted to show you there that look at this. Then this turns out to be the instantaneous velocity. At time t. But this, as you know, is the derivative. So the instantaneous velocity is equal to the derivative of s, my s function there. Yeah. Turns out another application of derivative, if you're talking distance function, height function, is the derivative is equal to the velocity. Okay? So if I'm talking this, this is the height. What's the height? What is the velocity of this object after 2 seconds, or at 2 seconds? Talking instantaneous velocity. Well, the velocity turns out to be the derivative of your distance function. So the derivative is 70 minus 32t. So at 2 seconds, the derivative is 70 minus 32 times 2. That would be 70 minus 64, just 6 feet per second. So this is a very easy problem now. Like I said, back when we last visited this problem, we did these average velocities with a table, and then looked to see what it looked to be going to. Well, now we can just go. If we've got the equation, we can just go right to the velocity. All right. What about what's the velocity at 4 seconds? Just to make a little point here. Well, that would be 70 minus 32 times 4. And so that's 70 minus, what was that, 128? Negative 58 feet per second. And I was just going to mention that The negative, velocity is speed, but it's directed speed. What the negative means is it's going the opposite direction of what it was going here. This is a positive velocity. The negative velocity just means it's going in the opposite direction from what it was. Going here. Okay. All right. Another point here is that velocity can be thought of, it's a rate of change of the distance, right? It's the rate of change of the distance with respect to the time. Would you agree with that statement? That's what velocity is. It's the rate of change of the distance with respect to time. So, that is another way to think of, isn't velocity here, it's the derivative of the distance function? And so, another way we can think of derivative is it's a rate of change. And this isn't just one example. I mention that because we can do the same thing. This is just for the derivative of the distance. What if I have any function? Y equals f of x. Well, what would the derivative then represent? Well, it depends on what it represents, right? But what we can say in general is that the derivative represents rate of change. The derivative, the f prime, represents the rate of change of f with respect to x. WRT with respect to x. Rate of change of f with respect to x. Okay? Now also note the units of the derivative. Playing again off the velocity, what are the units of velocity? Well, in the one I had, it was feet over seconds. It was the distance divided by the time. Well, if I'm talking just any function, you're going to take the units of what your original function was and then divide it by the units of in this case to be the units of x divided by the units of your variable there. Just like here, when I had s was 70t minus 16t squared, s prime units. Well, it was the units of distance, units of s, divided by the units of t. Well, if it's just a regular function f, whatever function f it is, you take the units of f divided by the units of x, and it all goes back to that limit definition, really. It's the way it's arranged. Okay? So why do I say all that? Well, it's because if I have the number of bacteria in a culture after t hours to be y equals 2t squared plus 500. What does the derivative represent here? And what I would like for you to get in the habit of is just noting that the derivative is going to be this. It's going to be the rate of change. In this case, we're talking about the number of bacteria. So what does the derivative represent? It represents the rate of change of bacteria with respect to time. Okay, so if I find the derivative at hour 2, it's going to be the rate of change of the bacteria. How fast that bacteria is changing, the number of bacteria is changing. And then the units of y prime, what would the units of y prime be? Well, you take the units of your function, which is number of bacteria, divided by the units of your variable, which is time t, which is bacteria per hour, right? With me on that? Because t is in hours and bacteria is number of bacteria. One other thing let me mention. I'm cutting it close here, but I did want to mention one other thing. You know, I had S equals 70t minus 16t squared, and I said S prime is the velocity, which is the rate of the change of your distance, your height. Well, what if I did a second derivative? Well, the second derivative would be the rate of change of the first derivative, which is the velocity, right? Because you do a derivative, you get a rate of change. Well, if I do this derivative of the velocity, which, you know, here I'm going to get be negative 32, wouldn't it? But what I was going to say is, if you're talking about the rate of change of the velocity, that's like taking the accelerator, you're going along at a certain speed, you hit the gas, accelerate up, right? You're changing the rate of your velocity. Well, I gave it away there. I said you hit the accelerator. That's acceleration, isn't it? The rate of change of the velocity, that's acceleration, or deceleration if you're decelerating. So the second derivative of the distance function, that's acceleration. So the second derivative of